Mars is not the dead world we once imagined. Its surface shifts and changes with the seasons, marked by a haunting phenomenon. Dark, finger-like streaks flow down sun-warmed slopes, only to fade away when the cold returns. These are the recurring slope lineae, or RSL, the most tantalizing mystery on the red planet today. By the end of this, you will understand 20 profound puzzles that could redefine our search for life beyond Earth. Are these streaks proof of liquid water flowing on modern Mars, or is a completely dry, alien process at work? Why do they return to the exact same spot every single year? We are going to unravel each layer of this enigma, from the chemistry of strange salts to the strict rules that keep our rovers at a frustrating distance. What does it feel like to watch a planet that refuses to give up its secrets easily? These dark streaks are the very first piece of the puzzle, and they are far stranger than they look. Officially, they are known as recurring slope lineae. Let us break that down. Lineae simply means lines. Slope tells us where they appear, exclusively on the steep, sun-facing walls of craters and valleys. And recurring is the most important word of all. It means they come back every single Martian year when the local temperatures climb. These dark, narrow streaks begin to snake their way downhill. They can grow for months, extending hundreds of feet like fingers reaching for the valley floor. Then, as the season turns cold again, they slowly fade from view, only to reappear in the exact same place when warmth returns. This predictable, repeating behavior is what first caught the attention of scientists. It was the Mars Reconnaissance Orbiter, with its incredibly powerful HiRISE camera, that spotted them. This camera can see objects the size of a dinner table from orbit, and it revealed these streaks in stunning detail. They are not random stains or shadows. They are active, seasonal features that behave as if something is flowing just a tiny bit down those slopes. That single word, flowing, ignited the biggest mystery on Mars. Because on a world with an atmosphere so thin that liquid water should instantly boil or freeze, what could possibly be flowing? The discovery of something flowing immediately pointed toward one obvious suspect. Water. For decades, scientists had searched for any sign of liquid water on the modern Martian surface. Here, at last, was a phenomenon that acted just like it. This gave rise to the wet hypothesis, a compelling and hopeful idea. The thinking goes like this: Mars is incredibly cold, and its atmospheric pressure is so low that pure water would either freeze solid or evaporate almost instantly. But what if the water was not pure? What if it was a brine saturated with salts like perchlorates, which are known to exist in the Martian soil? These salts act like antifreeze. They can dramatically lower the freezing point of water, allowing it to remain liquid at temperatures far below zero. The wet hypothesis suggests that just beneath the surface, in these specific warm slopes, these salty brines lie dormant. When the season turns warm, the very top layer of this brine reservoir thaws and becomes liquid. It then seeps out at a point high on the slope, darkening the soil as it trickles downhill. The water itself would evaporate quickly into the thin air, but it leaves behind the damp, darker streak of disturbed grains. When the cold returns, the source brine refreezes, and the streak fades as dust settles over it. This idea was electrifying. Where there is liquid water, even salty, briny water, there is at least the potential for life as we know it. It suggested Mars might not be completely dry and dead, but could harbor tiny, habitable niches in its crust. But science thrives on skepticism, and an equally compelling counter-argument emerged: the dry flow hypothesis. This camp looks at the same dark streaks and sees no water at all. They propose a completely different mechanism, one of granular flow. Picture a steep hill of very fine, dry sand and dust. On Mars, the changing seasons cause dramatic shifts in temperature. As a slope warms, frozen carbon dioxide or dry ice, trapped just below the surface, can turn directly into a gas in a process called sublimation. This release of gas could gently destabilize the overlying layer of grains, causing them to avalanche downhill in a thin sheet. Alternatively, the heating and cooling itself might cause the grains to expand and contract, slowly shuffling them downward. These dry avalanches would darken the slope simply by revealing fresher, darker material underneath a layer of bright dust, or by arranging the grains in a way that absorbs more sunlight. No liquid required. This debate is not just academic bickering, it is fundamental. If the streaks are wet, we are looking at the most significant discovery in planetary science, evidence of liquid water actively shaping the Martian surface today. It redefines the planet's habitability. If they are dry, then Mars is far more arid and perhaps less hospitable than we dared hope. The entire future of Mars exploration, where we send our rovers and how we search for life, hinges on which of these two stories is true. And as we will see, the evidence has become frustratingly ambiguous, pointing in both directions at once. The hope for a clear answer led scientists to a powerful tool in orbit. Aboard the Mars Reconnaissance Orbiter, alongside that incredible camera, is an instrument called CRISM. Think of it not as an eye, but as a chemical tongue. It does not just see light, it tastes it. By analyzing the specific wavelengths of sunlight reflected from the Martian surface, CRISM can identify the unique spectral signatures of different minerals. If liquid water was flowing down those dark streaks, even briefly, it should leave a trace. It would alter the chemistry of the surface grains, creating hydrated minerals, or at the very least, leaving behind the clear fingerprint of salts like perchlorates. So scientists pointed CRISM at the recurring slope Lineae, expecting a eureka moment. The data came back and it was baffling. The streaks themselves showed no strong spectral signature of water or salt. They were, chemically speaking, almost identical to the surrounding dry slope. This was the spectral signature conundrum, a massive blow to the wet hypothesis. If water was flowing every year, why was it leaving no chemical trace? One possibility is that the water is incredibly fleeting. It might only seep out for minutes or hours, not long enough to chemically change the rocks before it evaporates into the thin air. Or perhaps the water flows just beneath a thin layer of dust, darkening the surface from below without ever directly touching the grains that CRISM can see. The other, more straightforward interpretation was that the dry flow hypothesis was correct all along. A dry avalanche of grains would not change the chemistry. It would just move existing material around, perfectly explaining the lack of a new spectral signal. This conundrum seemed to tilt the scales toward a dry Mars, but then the story twisted again. More recent and very careful re-examinations of the data have suggested something new. There might be extremely weak, tentative detections of perchlorate salts associated with some of these features. The signal is faint, inconsistent, and hotly debated. It is like hearing a whisper in a roaring wind. You are not entirely sure it was ever there. Yet if it is real, it adds a layer of maddening complexity. It could mean that water is involved, but in such a subtle, subsurface way that our orbital instruments are barely able to glimpse it. So the spectrometer did not solve the mystery, it deepened it, leaving us with a question that feels almost philosophical. How do you prove the existence of something that vanishes without a trace? The timing of these streaks is as precise as a celestial clock. They do not appear randomly, but follow a strict seasonal rhythm tied directly to the warmth of the Martian sun. This is the fourth mystery, the lockstep dance between temperature and activity. On Mars, a year is nearly twice as long as our own, and the recurring slope Lineae have a brief, intense growing season. They begin their slow crawl downhill during the local spring when the sun climbs higher in the sky. Their growth accelerates through the summer, reaching maximum length at the peak of the heat before fading away as autumn's chill sets in. They are almost exclusively found on equator-facing slopes, the warmest walls of canyons and craters that act as solar ovens, basking in the most direct sunlight. This perfect alignment points to a specific temperature threshold, a tipping point that awakens whatever process creates them. Scientists estimate this trigger happens when surface temperatures climb above about 250 Kelvin, which is around -20 degrees Celsius. That number is the key to the entire phenomenon. It is cold by our standards, but on Mars it is a significant warmth. So what happens at that magic number? The answer depends entirely on which hypothesis you follow. For the wet model, this temperature could be just enough to melt a thin layer of shallow subsurface ice, or more likely, to liquefy a briny sludge laced with perchlorate salts. The heat thaws a microscopic layer, allowing a damp trickle to emerge and darken the slope. In the dry model, the rising temperature does something completely different. It could be warming the surface grains enough to make them more mobile, reducing friction so they can slide. Or, more intriguingly, it might be sublimating frozen carbon dioxide trapped just below the surface. As the dry ice turns directly to gas, it lifts and destabilizes the overlying dust, triggering a silent, dry avalanche. Both stories fit the seasonal data perfectly. Both explain why the streaks vanish when it gets cold. This leaves us with a profound and simple question. What exactly is that warmth unlocking? Is it turning a key in a tiny, hidden lock of ice, or is it simply turning up the volume on a constant, whispering landslide of dust? The planet gives us the when and the where with perfect clarity, but it stubbornly withholds the why. That precise temperature threshold points directly to a strange and powerful chemistry. If water is the hidden actor in this seasonal drama, it cannot be the pure, clear water of Earth's streams. It would have to be a thick, toxic soup, saturated with salts that rewrite the rules of physics on Mars. This brings us to the fifth mystery, the role of salts and brines. The most notorious of these Martian salts are perchlorates. On Earth, these compounds are used in rocket fuel and are generally considered hazardous. On Mars, they are everywhere, woven into the very soil, and they have two extraordinary properties that make them the perfect suspect for creating recurring slope lineae. First, they are powerful antifreeze. When perchlorates dissolve in water, they create a brine that can stay liquid at temperatures far below the freezing point of pure water. We are talking about remaining a liquid down to -70 degrees Celsius. That magic number of -20 degrees Celsius, the temperature when the streaks start to flow, is positively balmy for a perchlorate brine. It could easily be liquid at that warmth. Second, these salts are hygroscopic, meaning they thirstily pull water vapor right out of the air. This leads to a process called deliquescence. Imagine a tiny crystal of salt sitting on a cold rock. As the morning sun warms the slope, the crystal begins to absorb microscopic water molecules directly from Mars's thin atmosphere. It drinks in the vapor until it dissolves itself into a tiny, sticky droplet of brine. That droplet could then connect with others, creating a damp film just beneath the surface dust. Scientists have tested this idea in Mars simulation chambers on Earth, recreating the planet's freezing temperatures and bone-dry air. They have watched as salts like calcium chloride and perchlorates did exactly that, forming dark, damp patches that slowly crept downhill, mimicking the behavior of the streaks. It is a compelling and eerie match. So the theory goes that on certain Martian slopes, these salts are concentrated just below the surface. When the seasonal warmth hits that critical point, they begin to deliquesce, pulling a meager supply of water from the atmosphere to form a microscopic layer of brine. This dampens the soil, reduces friction between grains, and allows a slow, gravity-driven flow to begin. The water would evaporate quickly, but the salt remains, ready to repeat the cycle the next year. This brine hypothesis elegantly explains how liquid could exist in a place where it should be impossible. It turns the planet's thin atmosphere from an obstacle into a potential water source. But it also paints a stark picture. Any liquid water on Mars today would not be a pristine oasis. It would be a corrosive, freezing, super salty sludge, a harsh environment that would push the limits of any potential life. The salts are both the enabling clue and a warning, showing us a path for water to exist, but in a form more alien than we ever imagined. The geography of these streaks is a map to their secret. They are not scattered randomly across the rust-red plains. Recurring slope lineae are fussy, selective tenants, choosing only the most dramatic real estate Mars has to offer. You will find them exclusively on steep, rugged slopes, the kind that would give a rover pause. They favor the sun-baked inner walls of massive craters, the sheer cliffs of the Great Canyon system Valles Marineris, and the rocky flanks of isolated mountains and central peaks. Their addresses are almost entirely in the planet's mid-latitudes and equatorial regions, the warmer belts of Mars. This is no coincidence. The placement is a critical clue, a set of strict environmental requirements that any explanation must satisfy. Think of these slopes as solar collectors. Their steep, equator-facing angles are perfectly tilted to catch the maximum amount of sunlight during the Martian spring and summer. This geometry creates localized hotspots, little ovens where temperatures can spike just enough to reach that critical threshold, whether it is for melting a brine or triggering a dry avalanche. But the story goes deeper than just warmth. The specific geology of these slopes likely plays a role. Crater walls and canyon sides are essentially giant cross-sections of the Martian subsurface, exposing layers of rock and sediment that are buried elsewhere. Perhaps these layers contain the necessary reservoirs of ice or concentrated salts. Maybe the slope itself is just unstable enough, covered in a fine layer of dust and sand that is primed to move with the slightest nudge. Famous sites like the colossal Valles Marineris, a canyon system that could swallow the Grand Canyon whole, are hotbeds for these features. Here, the slopes are immense and sun-drenched, providing the perfect laboratory. Another prolific location is Hale Crater, where dozens of dark streaks paint the crater's inner walls each summer. By studying these specific sites, scientists are trying to reverse engineer the recipe. Is it the angle of the slope, the composition of the soil, the presence of certain minerals, or a precise combination of all three? The geography tells us that whatever creates these streaks is not a global process, but a local one, triggered by a very special alignment of factors found only in these rugged, sunlit places. It is as if Mars is whispering that the answer is not just in the chemistry or the temperature, but in the very lay of the land. The geography is fixed, the timing is precise, and so too is the life cycle of each individual streak. This is not a chaotic event, but a slow, patient rhythm of darkening and fading that plays out over months. A recurring slope lineae begins its life as a faint, indistinct smudge high on a warm slope. As the season progresses, that smudge begins to lengthen like a shadow stretching in the late afternoon sun. It snakes its way downhill, sometimes branching into tributaries, advancing at a rate of a few meters per day. Over weeks and months, a single streak can grow to an astonishing length, reaching hundreds of meters down the crater wall. It is a slow, relentless creep, a visible change on a planetary scale that we can watch from orbit. The darkening is thought to be caused by the disturbance itself. Whether it is a damp trickle or a dry avalanche, the process exposes fresh material from beneath a thin layer of bright, dusty rust. It is like drawing a finger through the dust on a car, revealing a darker, cleaner line underneath. But this growth is not permanent. As the peak of summer passes and the slope begins to cool, the process reverses. The dark streak does not vanish overnight. It slowly fades, becoming fainter and grainier until it blends back into the surrounding terrain, often disappearing completely by the time winter arrives. So what causes this fading? The explanations again split along the wet and dry divide. If the streak is formed by a briny flow, the fading could be the final act of evaporation. The last remnants of moisture vanish into the thin air, leaving the salts behind. Then the relentless Martian wind begins its work, slowly sprinkling a new layer of fine, bright dust over the dark track, burying it until the next cycle. In the dry hypothesis, the fading is simpler. The avalanche of dark grains has stopped, without fresh material being constantly exposed. The natural processes of dust deposition, and perhaps even the gentle shifting of grains in the wind, work to recover the streak, restoring the slope to a uniform, bright state. The most mesmerizing part of this cycle is its repetition. The next Martian year, when the sun returns to that same slope and the temperature crosses that critical threshold, the streak reappears. Not exactly pixel for pixel, but in roughly the same place, following a very similar path down the mountain. This annual return is the heart of the mystery. It tells us this is not a one-time landslide or a random stain. Something is being replenished. In the wet model, it suggests a stable, subsurface reservoir of ice or brine that is tapped each summer, then sealed by the winter freeze. In the dry model, it implies a slope that is perpetually unstable, its surface layer of fine grains constantly poised to slide whenever the conditions are just right, year after year after year. The cycle itself is a clue written in time, a promise that the secret, whatever it is, will be back for us to see again. That annual return is the most compelling piece of evidence we have. These dark lines do not just appear somewhere warm, they come back to the exact same gullies, the same rocky alcoves, season after season. High above Mars, the HiRISE camera has been watching, creating a time lapse over years that reveals an astonishing pattern. A streak will darken a specific channel on the crater wall in year 1. It fades. The next Martian spring, a new streak emerges, not from a random new spot, but from that very same starting point, often tracing an almost identical path downhill. This is not a suggestion, it is a documented fact. The recurrence is real and it is precise. This behavior places a massive constraint on any theory trying to explain them. A random dust avalanche triggered by a passing dust devil or a random rockfall would not have this kind of loyalty. You would expect new streaks to form in different places each year, wherever the slope was most unstable at that moment. The fact that they are so faithful to their location screams that something is anchored there. Something in that specific spot is being reactivated by the seasonal warmth. Think of it like a hidden tap buried deep within the slope. When the sun hits it just right, the tap turns on and the flow begins. When winter comes, the tap freezes shut. The next year, the same tap thaws and opens again. This points irresistibly toward a persistent, localized source. What could that source be? The most dramatic possibility is a stable aquifer. A layer of porous rock, saturated with briny water, could lie just beneath the surface. A crack or a permeable layer in the rock could act as that tap, allowing a slow seep each summer. The water would not need to be a vast ocean, just a damp layer, a few centimeters thick, trapped by an impermeable seal of ice or clay. Another idea involves the seasonal cycle of frost. Mars' thin atmosphere contains water vapor. In the cold winter, this vapor could freeze directly onto the cold slopes as a thin layer of frost, perhaps mixed with dust. When spring arrives, this frost layer warms and sublimates, turning directly to gas. That release of vapor could mobilize the dust, creating a dry flow, but one that is tied to the exact spot where the frost accumulated most thickly. Or the source could be geological. Perhaps there is a specific layer in that slope, rich in salts or with just the right grain size, that becomes unstable every single year when it reaches a certain temperature. It is a weak layer that fails predictably, like clockwork. This consistency is the strongest argument against purely random, dry processes. While a dry avalanche could theoretically recur in the same place if the slope's structure dictated it, the annual precision feels more like a system being triggered than a slope simply collapsing. It feels intentional, even though it is purely mechanical. This mystery of the returning streak forces us to look beneath the surface, to imagine the hidden architecture of Mars. It tells us that the answer is not blowing in the wind, but is locked in the ground, waiting for its annual moment in the sun. That precise annual return leaves a visible mark, a darkening of the slope that we can see from millions of miles away. But what are we actually seeing? This is the darkening mechanism, the visual heart of the mystery. The change in color is our primary clue, and it is surprisingly complex. A bright, dusty slope turns dark, and that simple observation branches into multiple competing explanations, each with its own story. The first and most intuitive idea comes from the wet hypothesis. Think of a dry, light-colored beach. If you pour a little water on it, the sand instantly darkens. This happens because water fills the tiny spaces between the grains, reducing the scattering of light and allowing the material to absorb more. If a briny seep is emerging on Mars, even a microscopically thin film, it could darken the surface in exactly this way. The dampened soil would appear strikingly darker against the dry, bright surroundings, a phenomenon we can easily recreate in a lab. But there is a compelling dry alternative. Mars is famously dusty, covered in a fine, rust-colored powder that is highly reflective. Imagine that same bright slope. If a thin layer of this bright dust were to slide away, what would it reveal? The underlying material, the actual bedrock or coarser sand beneath, is often much darker. A dry granular flow, a silent avalanche of just a millimeter of surface grains, could act like a cosmic eraser, scrubbing away the bright coating to expose a darker layer underneath. No liquid required. The third possibility is more subtle, a change in the texture itself. Sometimes, when fine grains get damp and then dry out, they can form a thin, cohesive crust. Alternatively, the flow process itself might sort the grains by size or pack them more tightly. Both of these actions change the way light reflects off the surface. A crust or a densely packed layer will often appear darker because it has fewer tiny air pockets to scatter light. It is the difference between fluffy, bright snow and hard, dark ice. So the dark streak we see from orbit could be a crusty seal left behind by a vanished trickle, or simply a rearranged bed of grains from a dry slide. This single visual clue, the darkening, refuses to point to one answer. It is a shapeshifter perfectly explained by both water and wind. It forces us to ask a deeper question. Are we looking at a stain, a scratch, or a scar? The distinction is everything, and from orbit we simply cannot tell. The dark streak itself is only the visible trail of a hidden beginning. To solve this, we must find where it starts. This is the hunt for the source, the elusive head of the recurring slope Lineae. From orbit, scientists trace each dark finger back uphill, looking for the precise point where it first appears. The answer is not simple. Most do not seem to spring from a single, pinpoint opening like a terrestrial spring. Instead, they often originate from a specific rocky outcrop, a distinct band of darker material, or a clear geological layer exposed on the slope. It is as if the entire layer is sweating, weeping a dark line from its entire length rather than from one single pore. This pattern is a critical clue. A single spring would suggest a concentrated pipe-like channel from deep below. A linear source, however, points to something more distributed. It suggests a reservoir or a condition that exists along that entire layer. Imagine a layer of rock rich in salts lying just a meter beneath the surface. When the seasonal warmth penetrates to that depth, the entire layer could become active, releasing a tiny amount of moisture along its entire exposed edge. That dampening would then trigger a flow that consolidates into a few main streaks as it moves downhill. Alternatively, the source could be a shallow layer of ice protected by a thin blanket of dust. As the sun warms that specific band on the crater wall, the very top of that ice layer sublimates or melts, destabilizing the overlying soil and starting an avalanche along a line. The hunt for this source region is the key to the entire mystery. If we could just see what is at that starting line, we would know, is it a visibly damp patch? A glint of ice, a crust of white salt, orbital images give us hints, but they cannot provide the definitive, close-up chemistry we desperately need. This is why the source remains a ghost, a theoretical necessity we can infer but not yet touch. Finding it would tell us if Mars is secretly wet or just endlessly, dryly shedding its skin. Finding the source is a scientific imperative, but it is also a profound ethical dilemma. This brings us to a mystery that is not about Mars alone, but about us, and the rules we must follow as we explore. If there is even the slightest chance that recurring slope lineae are formed by liquid water, then these dark streaks fall into a category known as special regions. The definition is strict and carries immense weight. A special region is any place on Mars where terrestrial organisms, microbes hitchhiking from Earth on our spacecraft, could possibly survive and replicate. The presence of liquid water, even a briny trickle, would provide the one thing those hardy Earth germs need most, a chance to live. The risk is not to Mars but to our own quest. If we were to drive a rover covered in Earth bacteria into a damp streak, we could irrevocably contaminate that site. Any potential signs of ancient or even extant Martian life we might later discover there would be forever suspect. Did it come from Mars or did we bring it with us? That question would haunt science for generations. Because of this, planetary protection is not a suggestion. It is a law of interplanetary exploration enforced by international treaty. Rovers like Curiosity and Perseverance, for all their incredible capabilities, are meticulously sterilized before launch, but they are not sterile. They carry a microbial zoo of Earth life in their cracks and crevices. As a result, they are categorically forbidden from approaching any designated special region, including the alluring slopes marked by recurring slope lineae. You can imagine the frustration. We have these magnificent robotic geologists equipped with drills and chemical laboratories sitting on Mars right now. They could drive to a dark streak, taste the soil, sniff the air, and likely solve the wet versus dry debate in a single afternoon. But they cannot. They must watch from a safe distance, their instruments pointed away, while the greatest mystery on the planet flows silently just over the next ridge. This protocol creates a catch-22 of cosmic proportions. To confirm if a site is a special region, we need to go there and check for liquid water. But we are not allowed to go there until we confirm it is not a special region. It is a perfect, maddening loop, so we are forced to be detectives working a crime scene from behind a police line, relying on orbital clues and distant observations, all while the answer sits tantalizingly out of reach. This barrier transforms the mystery from a purely scientific puzzle into a test of our patience and our principles. How far are we willing to go to find an answer, and what are we willing to risk? This perfect, maddening loop forces scientists to become detectives of the impossible, searching for answers in the one place they can freely explore. The key to unlocking Mars might be hidden right here on Earth. Our own planet holds landscapes so harsh and alien they serve as perfect stand-ins for the red planet, and these are the analog sites. The most famous is Chile's Atacama Desert, the driest non-polar place on Earth. Here, it can go decades without a single drop of rain, yet in its hyper-arid core, something remarkable happens. When the rare fog rolls in, salts in the soil greedily drink moisture from the air. They deliquesce, forming tiny droplets of brine that darken the soil. These damp patches then creep slowly down slopes, creating dark streaks that look, from a satellite's eye, almost identical to the recurring slope lineae on Mars. It is a stunning parallel, a dry desert mimicking a potentially damp process on another world. Then there are the McMurdo dry valleys of Antarctica, a frozen desert locked in perpetual cold. Here, scientists find seeps of super salty water that ooze from cliff faces, leaving behind dark stains of hydrated salts. They have even discovered microbes living within these brines, tiny life forms clinging to existence in a place with no liquid water for most of the year. These terrestrial analogues are not just curiosities, they are our most vital laboratories. When a new instrument is designed to detect brine or analyze soil chemistry for a future Mars mission, it is tested first in the Atacama or the dry valleys. Scientists can physically dig into these streaks, take samples, set up sensors, and watch the process unfold in real time. They can answer questions that orbiters never could. How fast does the brine actually flow? How deep does the moisture penetrate? What is the exact salt chemistry that makes it possible? And crucially, if life exists in these extreme spots on Earth, what does that imply for similar niches on Mars? By studying these earthly twins, researchers can refine the wet hypothesis with real data. They can also test the dry flow idea, watching how fine dust avalanches on sun-baked slopes create similar dark tracks without a hint of moisture. These analogues provide the ground truth that Mars withholds, allowing us to run experiments, make mistakes, and build confidence in our theories. They tell us that the processes we imagine on Mars are not just speculative fantasy. They are physical possibilities that play out in the most forgotten corners of our own world. Earth's deserts give us clues, but Mars has its own active weather, and that introduces another suspect in this mystery. Could the swirling, dust-filled tornadoes that race across the plains be the artists behind these dark streaks? This is the alternative hypothesis that dust devils create recurring slope lineae. Dust devils are a common sight on Mars, spinning columns of wind that can be many times larger than their earthly cousins. They act like cosmic vacuum cleaners, scouring the bright surface dust and exposing the darker material underneath, leaving behind long, looping tracks that crisscross the landscape. At first glance, it seems plausible. A dust devil dancing up a warm slope could, in theory, create a dark line. But when you look closer, the details tell a very different story. The tracks left by dust devils have a distinct personality. They are often broader, more curvilinear, and whimsical in their path, like a child's scribble. They follow the wind's chaotic dance, not gravity's straight pull. Most importantly, dust devil tracks are not strictly seasonal. They can form anytime the conditions are right for a whirlwind, and they almost never recur in the exact same narrow channel year after year. A dust devil track is a one-time event, a scar that slowly fades as new dust settles, not a feature with a precise annual clock. Compare that to the recurring slope lineae. These are narrow, gravity-fed fingers that flow straight down the steepest path. They are slaves to the seasons, appearing and vanishing on a schedule tied to temperature, not wind. And their most defining trait, their faithful return to the same starting point, is something a random atmospheric vortex simply cannot explain. While most scientists agree that dust devils are not the primary cause of the recurring slope lineae, they may still play a supporting role in the story. On a slope already primed for movement, perhaps by the subtle effects of sublimating carbon dioxide or thermal stress, a passing dust devil could provide the final nudge. It might kick off a small avalanche or clear a key patch of dust that then triggers a larger flow. In this way, dust devils could be occasional collaborators in the process, adding to the complexity of slope activity without being the main driver. So the dust devil hypothesis, while creative, ultimately fails to match the core evidence. It cannot account for the seasonal lockstep or the precise recurrence. It reminds us that on Mars, many processes are at work, painting the surface in different ways. The true culprit behind these dark streaks must be something far more anchored, something tied not to the whims of the wind, but to the very heartbeat of the planet's hidden geology. Dust devils are fleeting artists, but the true canvas of Mars lies hidden beneath the surface. To understand the recurring slope lineae, we must look deeper into the planet's frozen vaults. This is the 14th mystery, the potential role of subsurface ice. Mars is not a dry world through and through. We know it possesses enormous reservoirs of water ice, not just at the poles, but buried underground across its mid-latitudes. Orbital radar has mapped these layers, revealing ice sheets just a meter or two below the dust in some regions. This discovery paints a new and compelling picture for the wet hypothesis. Imagine one of those steep, sun-facing crater walls. Just beneath its surface, locked in the cold soil, is a solid sheet of clean water ice. When the Martian summer sun beats down on that slope, its heat penetrates the thin, insulating blanket of dust. The temperature at the very interface, right where the soil meets the ice, climbs above freezing. Only the top millimeter, perhaps just a few grains deep, begins to melt. It is not a gushing stream, but the birth of a microscopic film of liquid water, a vanishingly thin layer between the grains and the ice below. This meltwater, however brief its existence, could be the catalyst. It lubricates the soil, reducing friction dramatically. Suddenly, that entire top layer of dust and sand, now slightly damp and heavy, becomes unstable. Gravity takes over, and it begins to slide down the steep incline in a silent avalanche. The movement exposes the darker material underneath or creates a damp, dark track as it flows. As soon as the slide moves the damp soil away, the process stops. The fresh surface is dry, and the ice table remains intact, sealed again until the next summer when the sun returns to melt another microscopic film. This model is beautifully simple and directly ties the streaks to Mars's global water cycle. It explains the strict seasonality, the recurrence in the same spots, and the preference for warm, steep slopes. The ice table is the persistent source, the sun is the annual trigger, and the resulting flow is the dark streak we see. But this elegant idea immediately runs into complications. Radar data suggests these shallow ice deposits are widespread, yet recurring slope lineae are not. They are picky, appearing only on select slopes within ice-rich regions. So why does the ice melt only in those specific gullies and not everywhere? The answer may lie in the slope's angle and composition. A perfectly vertical sunbeam on a flat surface delivers less energy per square inch than one striking a steep, tilted slope head-on. The geometry matters. A crater wall tilted directly toward the equator acts like a solar panel, absorbing maximum heat to reach that critical melting point, while a gentler slope nearby might not. Furthermore, the insulating dust layer must be just the right thickness. Too thick and the sun's heat never reaches the ice. Too thin and the ice may have sublimated away entirely. There is also the question of purity. If the ice is mixed heavily with soil and salts, its melting point drops, changing the entire thermal equation. This subsurface ice model offers a powerful framework, but it transforms the mystery. It is no longer just about what is flowing on the surface, but about mapping the invisible architecture of ice just beneath our feet and understanding why, on a planet of hidden oceans, only certain windows frost over and weep. The ice table is a compelling source, but what if the water does not come from below at all? Mars holds its moisture in the air, a ghostly whisper of vapor in its thin, cold atmosphere. This leads us to a fascinating possibility where the atmosphere itself becomes the provider. The process is called deliquescence, and it is a quiet, almost magical chemical trick. Picture a single grain of salt on a sun-drenched rock. As the morning light warms the slope, that salt grain begins to thirst. It reaches out not to a puddle or a stream, but directly into the thin Martian air, pulling individual water molecules toward itself. One by one, these molecules stick to the salt, dissolving its outer layer until the entire grain transforms into a microscopic, sticky droplet of brine. It is a self-made oasis, a droplet born from nothing but air and chemistry. On a slope covered with such salts, billions of these tiny droplets could form, creating a network of dampness just between the grains of soil. This damp film, even if it is only a few molecules thick, could be enough. It might darken the surface by changing how light reflects, or more importantly, it could act as a lubricant. When a thin layer of dust becomes slightly damp, the friction between grains plummets. what was a stable slope becomes a sheet on the verge of sliding. The gentle, persistent pull of gravity does the rest, initiating a slow, granular flow that carves the dark streak we see from orbit. This atmospheric model is elegant because it sidesteps the need for a hidden aquifer or a shallow ice table. The water source is everywhere and nowhere, a diffuse vapor harvested by clever salts on demand, but it comes with its own strict set of requirements. For deliquescence to work, the local humidity must be just right, and the temperature must hit a very specific sweet spot. It cannot be too cold or the vapor will not gather, and it cannot be too warm or any droplet that forms will evaporate instantly in the thin air. This need for perfect conditions could explain why recurring slope lineae are so picky about their locations. Only on those precise equator-facing slopes at that exact time of year do temperature and humidity briefly align to create this ephemeral dampness. It is a fleeting window of possibility that opens and closes with the seasons. This theory turns the entire landscape into a collection of silent chemical sensors, each slope testing the air and responding with a dark line when the moment is perfect. It suggests a Mars that is actively trading water with its own surface in the most subtle way imaginable, painting its hillsides with the brush of its own thin, dry breath. The possibility of water, however fleeting, forces us to confront a question that changes everything. Could these dark streaks be more than a geological curiosity? Could they be a home? This is the profound mystery of modern life on Mars, the ultimate implication of the wet hypothesis. If recurring slope lineae are indeed formed by briny seeps, then they represent a potential habitat, a niche where Martian microorganisms, if they exist, could cling to survival today. It is a staggering thought that we might be looking at the address for life on another world, written in streaks across a canyon wall. To even consider it, we must look to the most extreme survivors on our own planet, organisms that redefine what it means to be alive. In the hypersaline ponds of Antarctica, where the water is colder and saltier than seawater, bacteria and archaea thrive. Within the seemingly barren rocks of the Atacama Desert, microscopic endoliths live inside pores and cracks, harvesting minuscule traces of moisture and nutrients from the stone itself. These are not complex creatures, they are masters of patience, capable of entering states of suspended animation for decades, only to reawaken when a rare liquid water event passes through. If life exists within the recurring slope lineae, it would likely be this type, a simple, salt-loving, rock-dwelling extremophile. It would face a brutal existence. Its world would be a cycle of feast and famine dictated by the Martian seasons. For a few months each year, as the streak darkens, there might be a microscopic film of brine, a toxic soup of perchlorates but liquid nonetheless. During this window, metabolism could briefly flicker. Nutrients might be scavenged from the soil, or energy could be drawn directly from chemical reactions between the salts and the rock. Then, as the cold returns and the brine evaporates or refreezes, life would have to shut down completely, entering a deep freeze, waiting in stasis for the next brief summer. The environment would be punishingly harsh, bathed in radiation, devoid of organic richness and subject to wild temperature swings. Yet on Earth, we find life in places we once thought sterile, from deep-sea hydrothermal vents to nuclear waste sites. The recurring slope lineae offer something those places have, a periodic return of liquid water. That regularity is key. It is not a one-time accident, but a reliable, if harsh, rhythm. A resilient microbe could theoretically synchronize its biological clock to that rhythm, waking with the flow and sleeping with the freeze, generation after generation. The search for such life would not be for green fields or crawling creatures, but for the faintest biochemical signature, a complex molecule or an odd isotope ratio in the soil of the streak that hints at a process beyond pure geology. To find it would be to discover that life is not a singular miracle of Earth, but a natural phenomenon, a process that can ignite wherever the universe provides the barest, most unforgiving chance. This search for life, however, remains a distant dream trapped behind a wall of profound frustration. We have been watching these dark streaks for years, mapping their every move from orbit, yet their fundamental nature remains a secret. The 17th and perhaps most human mystery is the challenge of in situ exploration, the simple, maddening fact that we cannot go and touch them. Orbital data has brought us this far, but it has also revealed its own stark limitations. From hundreds of kilometers above, we can see a slope darken, we can measure its temperature, and we can even glimpse hints of its chemistry. But we are like art critics trying to understand a masterpiece by staring at a photograph. We cannot feel the texture of the soil, we cannot scoop a sample into a cup, and we cannot press a sensor directly into the heart of the dark line to ask it the most basic question: are you wet? This distance creates an ocean of uncertainty. A spectrometer signature from orbit is an average over a large area, blending the signal of the streak with the surrounding terrain. It might miss a thin, crusty layer of salt or a microscopic dampness that would be obvious to a robot's arm on the ground. We are trying to solve a chemistry exam by looking at the classroom from a satellite, and it simply cannot be done. The obvious solution is to send a rover, but here the dream crashes into the twin barriers of engineering and ethics. First, the engineering. Recurring slope lineae form on steep, unstable slopes, often littered with boulders and loose material. These are treacherous landscapes, the kind that could trap or topple even the most capable rover. Designing a machine that can safely ascend a 30-degree incline of slippery dust, drill into it, and conduct delicate experiments is a monumental challenge. But the greater barrier is not engineering, it is principal planetary protection. As discussed, these sites are potential special regions. Sending a rover that has not been sterilized to an unimaginable degree risks contaminating them forever with earthly microbes. The sterilization process for such a mission, known as Category 4C, is exhaustive and would add immense cost and complexity. It means baking every component, sealing every circuit, and ensuring that the chance of a single viable Earth organism reaching that streak is virtually zero. Our current rovers, for all their cleanliness, do not meet this standard, so they are legally and ethically forbidden from driving up to an active flow. They must observe from a safe, often frustrating distance, their instruments forever pointed at safer, drier ground. This impasse has forced mission planners to think creatively, to design the tools that might finally crack the case. Future mission concepts are now on the drawing boards, each a clever workaround to the contamination problem. One leading idea involves small, agile helicopters, like the Ingenuity drone that flew on Mars but with a scientific payload. A sterilized helicopter could lift off from a safe landing pad, fly directly to a streak, hover above it, and lower a sterilized sampling arm or sensor on a tether. It could taste the soil without ever landing, minimizing contact and leaving the site pristine. Another concept is a dedicated, heavily sterilized gecko rover that uses gripping claws or wheels to cling to steep slopes, equipped with a sealed drill that could pull a core sample from within the streak and analyze it in a self-contained, sterile laboratory on board. There are even proposals for impactor probes, small, sterile penetrators that could be fired from orbit to slam into a slope near a streak, throwing up material that could be analyzed by a nearby rover or lander. The goal of all these concepts is the same: to get a definitive in situ measurement, to press a hygrometer into the soil and measure its water content directly. To heat a sample in an oven and see if water vapor is released, to look at the grains under a microscope and see if they are cemented by salt crystals. One single, direct measurement from the right spot could end decades of debate overnight. The answer is so close, yet it remains locked behind the glass of our orbital observatories. It is a testament to both our ambition and our restraint, a puzzle we are desperate to solve but refuse to solve at any cost. We are waiting for the right messenger, a machine built with enough caution to protect a world and enough curiosity to finally ask a simple question of the dark lines on a sun-warmed slope. The dark lines on Mars feel uniquely alien, a signature of a world caught between desert and ice. But is this phenomenon truly a Martian fingerprint, or could it be a cosmic script written on other worlds as well? This mystery pushes our gaze beyond the red horizon to ask if recurring slope lineae are unique to Mars. To find out, we must become solar system detectives, searching for similar dark streaks in the family album of our neighboring planets and moons. Our first stop is the closest, our own moon. In the permanent shadows of lunar craters where temperatures are among the coldest in the solar system, orbital cameras have spotted something intriguing. Dark, narrow streaks staining the crater walls. At first glance, they bear a haunting resemblance to their Martian cousins, but the moon is far drier and more airless than Mars. There is no atmosphere to speak of, no seasonal cycle of frost, and likely no lingering water ice in these sunless pits. So what could be flowing? The leading suspect is completely dry. These lunar features are likely created by avalanches of extremely fine, dark dust, triggered by tiny moonquakes or the thermal stress of nearby sunlight hitting the crater rim. They are a reminder that dark streaks can be painted by gravity and dust alone, a cautionary note for anyone hoping every such feature means water. Further out in the asteroid belt lies the dwarf planet Ceres. Here, the story gets more interesting. Ceres is an icy world, and its surface is dotted with mysterious bright spots and dark stains. NASA's Dawn spacecraft observed dark material sliding down the slopes of craters like Crater. These flows are thought to be caused by brines, not of water, but of salty mud rich in compounds like sodium carbonate. The internal heat of Ceres, perhaps from a remnant warm core, may allow these subsurface brines to remain liquid and occasionally seep to the surface. This is a wet process, but on a body with a different chemistry and internal engine than Mars. Then we have the icy moons like Saturn's Enceladus or Jupiter's Europa. Their surfaces are crisscrossed by dark, linear features, but these are often massive cracks and fractures from which plumes of water ice and vapor erupt into space. The flows here are not thin, seasonal seeps, but part of a global, subsurface ocean interacting with the icy crust. They operate on a scale and with an energy that makes the modest streaks on Mars look like faint whispers. So what does this cosmic survey tell us? It reveals that dark, flowing features are not unique, but the specific recipe for recurring slope lineae might be. Mars seems to occupy a special, narrow niche. It is cold enough to preserve ice and allow brines to exist, but warm enough and with just enough atmospheric pressure for seasonal temperature swings to trigger a change. It has the right salts, the right slope angles, and a history of water that left behind the ingredients. The moon is too dry and static. Ceres may be too icy and its processes too deep. The icy moons are too active and wet. Mars sits in the Goldilocks zone for this particular phenomenon, a world where all the conditions align to create these enigmatic, seasonal brushstrokes. This uniqueness makes the recurring slope lineae not just a Martian curiosity, but a benchmark. They represent a specific type of planetary activity, one that requires a precise and fragile balance of climate, chemistry, and geology. Finding them elsewhere would mean finding another world that walks that same delicate tightrope between desert and spring. Mars is not a static painting, but a world with a climate that breathes over eons. This long-term view reveals our 19th mystery, the relationship between these dark streaks and the planet's deep climatic rhythms. To understand it, we must step back from the annual cycle and look at a clock that ticks in 100,000-year increments driven by a wobble. Unlike Earth, whose axial tilt is stabilized by our large moon, Mars wobbles dramatically. Its tilt, or obliquity, can swing from as little as 15 degrees to as much as 35 degrees over cycles lasting hundreds of thousands of years. This is not a subtle shift, it is a climatic earthquake. When Mars's tilt is high, its poles are pointed more directly at the Sun for longer periods. The frozen polar caps, vast reservoirs of water and carbon dioxide ice, bake under the intense, sustained sunlight. They sublimate furiously, pumping enormous amounts of water vapor into the thin atmosphere. The entire planet's water cycle amplifies, frost forms more thickly at lower latitudes, and the atmosphere itself becomes temporarily thicker and wetter. Now place the recurring slope Lineae into this ancient, shifting world. During these high-tilt, wetter epochs, would the dark streaks have been different? The possibility is captivating. With more water vapor circulating globally, the process of deliquescence of salts drinking from the air could have been supercharged. Slopes that are now bone dry might have once glistened with seasonal dampness. The dark streaks could have been more numerous, darker, and flowed farther down mountainsides. They might have appeared on slopes that today are too cold or too dry to host them, painting a much more active planet. Conversely, during long periods of low obliquity, when the poles are colder and the atmosphere is even thinner and drier, the streaks might have retreated, becoming fainter or vanishing entirely from all but the most perfectly oriented slopes. This means the recurring slope Lineae we see today are not necessarily a permanent feature. They could be a snapshot, a reflection of Mars in its current moderately tilted state. By studying their distribution and activity, we are not just looking at a current geological process, we might be reading a chapter from the planet's climate history book. Each streak's location and vigor could be a clue locked in the present, telling us about the atmospheric conditions of the recent past. This transforms the streaks from a seasonal puzzle into a potential climate proxy. If we can model how they respond to today's conditions, we might be able to run the clock backwards, using evidence of ancient flows to reconstruct what the Martian atmosphere was like millennia ago. It adds a profound new layer to the mystery, asking not only what they are, but what they were, and what they will become when the planet's next great wobble begins. The planet's ancient wobbles remind us this mystery is alive, changing with every season and every new mission we send. Our final question looks forward to the next decade of discovery and the tools that will finally answer what these dark streaks truly are. The future of recurring slope Lineae research is a story of new eyes, new hands, and perhaps new boots on the ground. Leading the charge is the European Space Agency's Rosalind Franklin rover, a machine built with this very puzzle in mind. Its most powerful tool is a drill capable of reaching 2 meters below the surface, far deeper than any rover has gone before. While it will not be sent to an active streak due to planetary protection, its mission is foundational. By drilling into ancient, water-altered clays in a region called Oxia Planum, it will search for the chemical fingerprints of past life. Success there would prove that Mars was once habitable, raising the stakes for finding where life might persist today and informing how we might one day safely approach a modern seep. Alongside new rovers, we will have new sentinels in the sky. NASA and other space agencies are planning next-generation orbiters equipped with even more powerful spectrometers and radars. These instruments will peer at the streaks with unprecedented sensitivity, perhaps finally catching the definitive, if faint, spectral whisper of hydrated salts, or mapping the shallow ice tables with centimeter precision to see if they truly lie beneath the flowing fingers. But orbiters can only do so much. The definitive proof will require touching the streaks themselves, and for that, we need a new class of explorer. Imagine a small, sterilized helicopter, a descendant of ingenuity but carrying a science lab. It could lift off from a pristine landing zone, fly to an active streak, and lower a sensor package on a tether to kiss the soil without contaminating it. That package could take the crucial measurements we crave. A tiny hygrometer would measure the soil's moisture content in real time. A thermal probe would gauge the temperature gradient just beneath the surface. A miniature microscope could image the grains to see if they are cemented by salt or simply loose. A single, direct reading of high humidity or a visible damp crust would tilt the debate forever. Alternatively, a rugged, heavily sterilized climbing rover could anchor itself to a steep slope using a sealed drill to extract a core sample from within the dark line and analyze it in a totally self-contained laboratory onboard, preventing any earthly contamination from escaping. And then there is the human element. While likely still decades away, the first human explorers on Mars would bring a flexibility and intuition no robot can match. An astronaut in a sterilized suit could approach a recurring slope Lineae, kneel down and simply look. They could chip at a crust, feel the texture of the soil, and deploy a suite of handheld instruments with the decision-making power of a seasoned field geologist. They could follow a streak to its source and see, with their own eyes, if it emerges from a damp patch or a dry fracture. Human exploration represents the ultimate in situ investigation, turning a remote puzzle into a tangible, solvable riddle. The key experiments are clear, direct chemical analysis of the streak material compared to the surrounding soil, continuous temperature and humidity measurements over an entire seasonal cycle, and high-resolution subsurface imaging to see the layer that is actually moving. With these data, the centuries-old question of water on modern Mars would finally be laid to rest. There is a palpable optimism in the scientific community that this mystery, which has taunted us for years, is on the verge of being solved. The pieces are coming together, the missions are being designed, and the answer is written on those sun-warmed slopes, waiting for the right moment and the right tool to read it aloud. 20 layers of mystery now lie before us, each one a question mark written across the Martian landscape. We began with the dark streaks themselves, those seasonal fingers reaching down sun-warmed slopes, and plunged into the fundamental debate that defines them all, the agonizing choice between liquid water and dry granular flow. We saw how orbital spectrometers returned bafflingly empty chemical signatures, a silence that deepened the riddle rather than solving it. The strict seasonal clockwork tied their activity to a precise temperature threshold, pointing toward strange salts and brines that could defy the cold. Their geography mapped them to the steepest, most sun-drenched real estate, while their patient life cycle of growth and fading spoke of a hidden, replenishing source. That source remains a ghost, its nature locked away by the strict protocols of planetary protection, which keep our most powerful rovers at a frustrating and necessary distance. We searched for answers in Earth's own extreme deserts, where brines darken arid slopes, and considered the fleeting artistry of dust devils, only to find their tracks lacked the required loyalty. The possibility of shallow subsurface ice offered a compelling tap, while the quiet magic of deliquescence suggested the atmosphere itself could provide the moisture. This raised the ultimate, staggering implication, the chance that these streaks could be a modern habitat, a niche where life might cling to a brutal, seasonal rhythm. Yet proving any of this is hamstrung by the immense challenge of in situ exploration, a problem inspiring ingenious future missions from sterile helicopters to climbing rovers. We looked beyond Mars and found that while dark flows exist elsewhere, from the dry dust slides of the Moon to the muddy brines of Ceres, the specific recipe of the recurring slope Lineae seems uniquely Martian, a product of its delicate balance. And we saw how this entire phenomenon is likely a snapshot, a clue to the planet's deeper climatic story written in wobbling tilts over hundreds of thousands of years. Together, these 20 puzzles form a single, monumental enigma. The recurring slope Lineae are not just a geological feature, they are a symbol. They represent the very frontier of our understanding, the place where our knowledge of Mars runs into the hard, beautiful limits of what we can know from afar. They are the reason we keep looking, keep sending new eyes and new hands. Every new image from orbit, every experiment in a desert lab on Earth, every design for a future sterile probe brings us one incremental step closer. So the next time you look up and see that rusty dot in the night sky, remember the silent drama unfolding on its sunlit slopes. Picture those dark lines slowly lengthening, holding a secret that could redefine a world. The mystery is alive, and the robots we are building today are being crafted with the sole purpose of finally asking those dark streaks, face to face, what they truly are. The answer is out there, waiting in the Martian summer heat.